Good afternoon, everyone. My name is John Einkoff. I'm the lead product manager for Elastic MapReduce, which is Amazon's managed Hadoop service. I'm going to talk for about 15-20 minutes about big data at AWS and specifically Elastic MapReduce. And then we're very fortunate to have a speaker from Intel to talk about some of the very interesting things that Intel and Amazon are doing together to enable big data. I want to just say before I get started, I recognize this is the last session in a packed day. It's beautiful weather out, so we'll probably try to get through the material and, if possible, give you back 15 or 20 minutes to go and enjoy the weather, or you can check out the expo, which I believe starts at 5 o'clock, which is downstairs where lunch was served. So let's get started. I'm going to talk about 4 things. We're going to talk a little bit about big data. We're going to talk about some examples of organizations that have turned data into actionable information. We're going to talk a little bit about analytics and cloud computing. And then we're going to talk for a few minutes about the big data ecosystem, and in particular, Amazon or AWS data pipeline, which if you were here for the keynote this morning, you heard a little bit about. So first, let's talk a little bit about big data. I'm sure everybody in the room has heard the kind of cliche at this point pitch around the 3 V's, around volume, velocity, variety. I'm not going to do that. I'll spare you that. I think another way to think about big data is to think about the data lifecycle. So if you think about it in terms of these 4 stages, you've got generation of data, collection and storage of data, the analytics and the computation on that data, and then finally the collaboration and sharing of that data. And what we've seen over the last few years is that the cost of data generation has fallen dramatically. It's now very affordable to generate lots of data very, very quickly. And as a result, what we see is a bottleneck at stage 2, which is the collection and storage, and it follows through to analytics and again, collaboration and sharing. The result is what we see here in this chart. This is a chart put together by IDC and Gartner. In the orange, we're looking at the amount of data that is being generated, and in blue is the amount of data that is actually available and being used for analysis. There's clearly a very large gap here, and that's a problem. There's a big missed opportunity. What do you need to close that gap? So there's a few things that you really need. You need elastic and highly scalable infrastructure. You ideally want to pay for that without any big upfront capital expense. You only want to pay for what you use as you use it, and you want everything to be available with the click of a button or with a single API call. You want it available on demand. In other words, if you can have all of these things, you can remove the constraints that we looked at on the previous slide around the data lifecycle. So this is what we were looking at before. With the constraints removed, what we see is that this lifecycle is accelerated, and organizations are able to ask more questions of more data. They're more interesting questions. You can have hypotheses, test the hypothesis. If it's incorrect, you fail quickly, and it's very cheap. This whole process is accelerated. You get to insight a lot faster, and organizations are getting a lot of value out of that. So what we really need to contain big data or to get value out of big data are technologies and techniques for working productively with data at any scale. OK, so that's all I really want to say, super high level about big data. Let's talk a little bit about, we have 4 examples of organizations that are taking data and pulling out insight and information. So first example, Razorfish. This is a digital marketing company here in the United States. They work with companies all around the world. One example that I want to share with you today is they were working with a large big box retailer in the United States, and their client, this retailer, wanted to know who buys video games. Ultimately, what they wanted to do was serve advertisements to the users on their website that would entice the retailer's users to buy video games. So they want to serve up ads and have them be very effective. So what Razorfish helped this client do is to set up a process in the cloud that processes 3.5 billion records a day, 10 to 20 terabytes of clickstream logs, tens of millions of cookies. It's a lot of data. A lot of it is unstructured. A lot of it is existing in different places. They built the process that did this, and they got a number of insights out of them. One, perhaps not surprising, is people who buy large flat-screen TVs tend to buy video games. That's by itself maybe not that interesting. What was interesting is they were able to go much, much deeper, and they were able to get insight that ultimately allowed them to on the retailer's website, when customers are looking at specific movies and specific TV models, they're able to deliver up ads for specific video games. And what they found was that the return on ad spend went up 500%. The procurement time went down by 17,000%. And the comment from the client in this case was not that they weren't really so much talking about the reduction in cost or any of that stuff. What they talked about was the agility that it gave them, the ability to move really, really fast. So this reduction in procurement time allowed them to move a lot faster and try more hypotheses, try more experiments. OK, let's talk about a second example, Yelp. I think most people here are probably familiar with Yelp. A couple of years ago, Yelp wanted to know who is using our service. This is a basic question. A lot of companies want to know this. They wanted insight about their customers. And what's challenging is that Yelp was generating, and Yelp's users was generating a lot of data, but it's really difficult to get the signal and the value out of that data. One of the things that they were able to figure out by analyzing that data is that people were visiting the site on mobile devices. They figured this out a couple of years ago. This was really before a lot of companies had clued into the shift towards mobile. And as a result, Yelp was able to make investments in mobile that has served them very well over the last few years. So today, or in January 2013, they're serving 9.5 million unique mobile devices. And they've been able to invest in particular features and particular things on the site that have allowed them to succeed. And it all kind of comes back to this initial insight that they were able to pull out of many, many terabytes of log data. Let's look at another example, very different. Amazon has a public datasets program where we host datasets for free on the Amazon cloud. One of those datasets is the Common Crawl dataset. This is an open index of the entire web. There's a lot of data in there. It's a lot of very unstructured, very messy data. There's about 3.5 billion records the last time we looked at it. And again, as I mentioned, available to everybody for free. There's a lot of interesting things potentially that you might want to get out of that data set. And one of those might be a researcher who wants to know what is the impact of social networks on the internet. And not just the internet in this country, but the internet globally. So we had a researcher do this. And they wrote 300 lines of Ruby code. It took them 14 hours. And they were able to get to an interesting result. This is an example where they're dealing with a lot of very messy, unstructured data, many, many terabytes of data. And all you really need is a little bit of code and access to the resources that AWS provides. And they were able to get actionable insight out of that data. Let's look at one more example. This is in the public health space and kind of social media and public health. So what we're looking at here is a chart showing two things. In blue are tweets about the flu. The dotted black line are CDC data about actual incidences of the flu. And what is interesting here is that there's a very tight correlation between the two. And what I'm sure many people in the room probably already know is that the CDC and other organizations spend a lot of money to generate this data. It's very expensive, it's very time-consuming, it's very capital-intensive to generate the data. And what's interesting here is that this actionable info is actually available in freely available social media data on Twitter. Begs really interesting questions about, are there better ways for organizations like the CDC to be getting this information, getting it faster, getting it cheaper? OK, let's talk a little bit about analytics and cloud computing. So back to our data lifecycle chart here. AWS has a number of services that map to each of these components. I'm not going to spend too much time on each of them. I'll just kind of very quickly highlight some of them. On collection and storage, there's S3. This is our highly durable storage service. I think we very recently announced that we've hit, I think, 2 trillion objects in S3, well over 1 million peak requests per second. Absolutely enormous, highly durable storage system. Glacier is a cold storage. If you were in the keynote this morning, I think Andy talked about this a little bit. Extremely cheap, really great for backup of data. Anytime that you've got data that you don't want to throw away, but you want to keep, and it needs to be cheap. Storage gateway, Andy talked about that this morning. DynamoDB is our NoSQL offering. So columnar database, a single second server-side latency on reads and writes. Absolutely phenomenal performance. Really great for web apps and other applications where you need really fast access to the data. Redshift was announced just a few months ago. It's our data warehouse as a service offering. RDS is our relational database service, so this is the relational database as a service, basically. HBase is a NoSQL database that sits on top of Hadoop. I'll talk about it a little bit more detail a little bit later. Clearly, there are lots of options here for collecting the data. So analytics and computation, there's many, many options here. Two of the most common are EC2 and Elastic MapReduce. Elastic MapReduce is the managed Hadoop service that I happen to work on. Collaboration and sharing. Again, lots of services, EC2, S3, RDS, CloudFormation. Some of you may have attended the session on CloudFormation earlier. It's our content delivery service. Again, DynamoDB, Redshift, lots of options. Across all of these stages, you really want to look at what are you trying to do in your application and with your workload, and you pick the services and the tools that best map to that. And ultimately, you hopefully end up with a topology that makes the most sense for you. And finally, we have a service that was announced just a couple of months ago called AWS Data Pipeline. This is the service that helps you to schedule data-driven recurring workflows. I'll talk a little bit more about it in a moment, so I won't spend too much time on it now. OK, let's spend 2-3 minutes talking about Elastic MapReduce. This is the managed Hadoop service. Before I go into too much detail here, I'd like to, just with a quick show of hands, see how many of you have ever used Elastic MapReduce. OK, so I see maybe 25%, 30%. So we have some users in the room. The folks that didn't raise your hand, raise your hand if you're using Hadoop today? OK, so maybe a little bit less than half. OK, so let me kind of explain a little bit how it works. This is a simplistic view. I'm not going to get into a lot of detail here, but hopefully this will be enough for those of you that aren't familiar with EMR to get a sense of what it could do and why it might make sense for you. So first, you put your data and your code into S3. You then come to the EMR service, and you can use the command line. You can use the SDKs. You can use the APIs or the management console. You have a number of options there. And you make a couple of decisions. You decide what Hadoop distribution you want to run, and there's several options there for you. You decide how many nodes you want to provision in your cluster, so anything from 1 or 2 nodes to thousands of nodes. You tell us what types of nodes you want to use. So these are EC2 instances underneath. So you might decide for your cluster that you want high CPU, because maybe you're doing image processing. Or maybe you decide you want high storage nodes, because you have a lot of data. Those nodes come with 48 terabytes per node. You might use high memory. You might use standard. You might use a mixture, depending on what you're trying to do. You also tell the EMR service what applications you want to install on that cluster. So within the Hadoop ecosystem, there's a number of projects and applications that you can use for different purposes. Hive is a NoSQL data warehouse for Hadoop. Pig is great for data flow and scripting type workflows. HBase is the NoSQL offering. Then there's a variety of other Apache projects that you can run. There's non-Apache, but also open source. Ganglia, for example, is a monitoring application. Mahout is a machine learning library. And then there's a bunch of things that you get by default. You get R by default. You get Mahout by default. So there's a lot of stuff that you get in the cluster. Some of it comes by default. Some of it you choose. You basically tell EMR, I want this, this, and this. After you've made those decisions, the EMR service will grab the data, it will do the processing, and then it will put the results back into S3 wherever you told us to put where you want the data to go. You could pick it up as a human, or most often some downstream process would grab the data. Now, one of the things you can do that's really interesting is you can expand and shrink your cluster. You can do this manually. You can script this. And the reason that you might want to do this is, let's say you're using EMR and Hadoop to process a certain amount of data every day. But then let's say you have an idea or you have a hypothesis that you want to test against a month of data or a year of data or all of your data. You might take that cluster, which is steady state 20 nodes, and expand it to 1,000 nodes. And then when you're done with that hypothesis, you just bring it back down to 20, or you get rid of the cluster. We have many customers that will very often have steady state 20 or 30 nodes in the day, and then they'll have 500 or 1,000 at night. And it just continuously goes up and down. And it's based on how much data and what they're trying to do. Now, one of the other interesting things here is you can use spot nodes. So spot are unused EC2 instances that you bid on. So there's a spot market price, and then there's your bid price. And as long as your bid price is above the market price, you will get those nodes. And as a result, you end up paying pennies on the dollar. We have many EMR customers are actually saving on the order of 70 or 80% by using Spot. Now, you want to be careful about using Spot because if the market price changes, you can lose those nodes. So you might not want to use Spot for your master node. You might not want to use Spot on a cluster that has a mission-critical, tight SLA attached to it. So you want to be careful. It's a really great tool to save money and save time, but you want to be careful about it and architect appropriately. Another thing you can do is if the data is in S3, you can launch parallel clusters against the same data source. So an example of a customer that does this is Netflix. So they will have one cluster that they use for their continuously processing all of the data coming from the devices around the world that are streaming Netflix movies. So all of the data around latency and what people are looking at and what people are clicking on, all of that is streaming into the cloud and being processed by one massive Hadoop cluster. Then they have another cluster that their BI analysts use. And it's a different instance type, and it's a different size, and there's a different configuration. And then they have other clusters that they will spin up for specific jobs and specific hypotheses that they want to test. And the neat thing about this is that if you have these parallel clusters against the same data, you can tune and configure each cluster so that it is ideally configured for what it's doing. And maybe some of your clusters you have up all the time, and they never go away. Other clusters you spin up for a few hours for a particular hypothesis, and then you tear it down. It's really up to you. We want to provide that choice to you. As I mentioned, if you don't need the cluster anymore, you can tear it down. And like everything else with AWS, if you terminate the resources, you immediately stop paying. So this is interesting because we have customers like Weatherbill that are calculating and recalculating insurance prices. And I believe they only spin up a single cluster every month. They use thousands of nodes 1 or 2 days out of the month. And then the rest of the month, they're not using anything, and they're not paying for the resources during that period of the month. It's pretty phenomenal. It's very, very different, obviously, than what you can do outside of the cloud. And I'd be remiss to mention, if I didn't mention, that you don't have to use S3. You can also spin up your cluster and store everything on the local ephemeral disk on HDFS. And we have some customers that use HDFS on the local drives. Other customers use S3. Some use a mixture. Again, it really is up to you. And if you do have a lot of data and you want to keep it there for a long term, I would suggest taking a look at some of our larger, beefier instance types like high storage, which comes with 48 terabytes per node, I think 10 gig networking. There's a lot of really cool things. And it's really great if you are at the scale of a petabyte or more. And lastly, you can run all of this inside a virtual private cloud. So for anybody that's concerned about security and the confidentiality of the data, everything is supported in VPC, and it's a matter of selecting VPC from a dropdown. Our service started in 2009. Since then, we've launched a little over 5 million clusters. I think it's at 5.5 million now. The customers range from across all industries and all use cases. One of our biggest users is actually Amazon.com, which has something like 500 teams now using EMR to do everything from identifying fraudulent buyers and sellers, to routing of packages, to A/B testing the website. Many, many very interesting things that they're doing, and a lot of that is running on EMR. I'm kind of getting toward the end here. I want to encourage you to give it a try. Hadoop is not easy, but the whole goal of our service is to make it as easy as possible and to make it as performant as possible, and take a lot of the management mess out so that you can focus on getting the value out of the data. The cost to run a 100-node EMR cluster, if you want to try this yourself today, is $7.50 an hour. That's less than the cost of a movie ticket. You can do quite a lot of damage with 100 nodes for an hour. And obviously, the saying holds that what you can do with 100 nodes for an hour is the same as what you can do with 100 hours on one node. And that's one of the core reasons why people are so drawn to Hadoop and services like EMR. So the last section is on the big data ecosystem. One of the issues that our customers face is that they have data in many different locations. There's the data in different silos. Even just within AWS, we have lots of different services where data potentially could be stored. You've got DynamoDB, S3, HBase, you've got EMR, Redshift, RDS, and this is just a subset of where the data might be living. kind of the question that comes out of that is, well, how do I get my data into the cloud, into all of those different locations? AWS provides a number of mechanisms for you. One is that you can generate a lot of data just by running your apps on EC2. You can transfer data into S3 for free. You can upload very large objects using multi-part upload into S3. It makes it much easier if you've got lots of data and large objects. You can actually put your data on physical media and ship it to us. You can use Direct Connect, which allows you to lease a 1 or 10 gig line or multiple lines. This is especially useful if you have lots of data that's continuously moving in or out or both. And then we've got regional replication of AMIs and snapshots. And again, this is a subset of all of the different options. But depending on what you're trying to do, the amount of data, whether it's one time, whether it's continuous, there are different tools that are available for you. And you can let us know what you're trying to do, and we can try to work with you on that. So then the next question is, once you've got your data into the cloud, are you comfortable that you can get the data there? The question is, how do I integrate my data to get the maximum impact out of it? So an example might be of how you might want to pull data and move it from one place to another is, let's say you've got some hot data in DynamoDB. So this might be product data, dimension data, something you're using in a web app, and you're on some schedule backing it up to S3, where you've got some of your cold or kind of warmish data. That data is periodically being streamed into an HBase cluster on EMR. Maybe you're using it for some sort of analytic application or multiple analytic applications. Then you've got EMR clusters that are going to spin up to process and analyze that data. And maybe it also will integrate, ideally, data from an on-premise source, like a data warehouse. The result of that processing and that flow is some sort of structured output that you want to put into Redshift so that your analysts can query against it using SQL and the tools that they're comfortable with. What I've described here is relatively generic, but it kind of shows that there are many situations where you might want to have data in Dynamo that's moving into S3, that's then moving into EMR to be analyzed, and then some output is moving into Redshift. You're needing to move the data from one place to another. You're needing to process it and transform it. What would be really helpful is if there was a service that made all this easy. So Data Pipeline is designed to handle data-driven recurring workflows. It was announced in November. It's available now in US East. It will be available in other regions soon. This is kind of what a simple pipeline looks like. You've got an input data node, and this might be an on-premise data warehouse. It might be an S3 location. It could be, it could be DynamoDB. It could be something in HBase. Anyway, you have an input data node, and then you have an activity that you attach to that data node. And that activity might be something like an EMR job, so a Hadoop job. And then optionally, you could have an output data node. The output data node, just like the input data node, could be an S3 bucket, could be DynamoDB, it could be something on-premise. But this is what a simple pipeline looks like. And now you can make it a little bit more complicated by attaching precondition checks to the input data node. So you might set up a pipeline that actually checks the S3 location for the arrival of a file. And the pipeline won't start until that file appears. And then attached to the activity, you might want to have failure and delay notifications. You might want to set up control logic around if this, then so-and-so. And then again, you've got your output data node. And then obviously, you can make the pipeline as complex as you want to suit your needs. I want to thank you very much. I want to also invite you to, if you are curious about any of these services, you can check out the websites here, Elastic MapReduce, Data Pipeline, Big-Data. And now I want to introduce Girish Juneja from Intel, and we're going to queue up a video while we come up on stage. Thank you very much. Appreciate your time, and hope you enjoy the rest of the event.
One way of thinking about big data is data for competitive advantage for customers. One of the big challenges of dealing with big data is turning all of this data into information.
Schrödinger was able to spin up a 50,000 core supercomputer. That allowed him to synthesize over 100 million molecules in just 8 hours.
The AWS cloud makes supercomputer capacity by the hour available to everybody, with high-performance cluster computer instances powered by Intel Xeon E5 processors. In 60 minutes, NASA JPL builds gigapixel images from Mars, so scientists wait less and explore more.
There's several technologies that Intel and Amazon Web Services have incorporated into these high performance or cluster compute instances. Advanced vector extensions within the Intel Xeon E5 series processors really allows us to take and perform 2 operations within 1 clock cycle.
And the cloud provides high performance at low cost to customers. So rather than customers having to spend lots of capital on infrastructure that sits unused, when they're using the cloud, they pay only for what they use.
The most exciting thing about Intel and Amazon Web Services, now you can get high performance computing cost effectively.
That was great setup by John. I'll give you a brief preview of how Intel and Amazon Web Services are working together to make it easier for you to try out Amazon MapReduce and Hadoop. So, oftentimes question is asked, what should I use big data for? I did my log analysis, I did my, kind of usual use case. Is there a bigger value, bigger V vector to be derived out of this? And what we have seen is actually profoundly, important changes can be made if you get real value out of data. I'll give you a few examples. We worked with some customers that are using gene data analysis and essentially combining the genomics data with the clinical data in order to come up with gene markers that can help cure diseases. So, we are really talking about our healthcare and how we can all live better. We have seen customers come up with completely new business models where they used historical data sets that they had with some social media data sets in order to monetize or price things that earlier they were not even charging users for. So they have completely changed their business models. And then in many places across the globe, we have been working with companies and governments where the national transportation systems, the smart grid and power management systems are been modified based on the amount of sampling of data you can do from that sensor network and the kind of knowledge you can derive by analyzing that data. So it is much more than log analysis, much more than kind of common mundane use cases you think and hear about Hadoop that you can do if the technology is available at scale in a way that it can be set up and tear down the way you can do on Amazon Web Services. So, this is where what I'll talk about is how we are helping the infrastructure to allow for unlocking of value that is there in some of the optimizations we are putting in silicon, how we are supporting open platforms so that the cost of doing this analysis comes down, eventually in order to deliver the kind of business value I discussed. And why Intel, right? You would think Intel is a silicon company and how close they are to actually understanding value from data. So this is kind of to give you a perspective. We have been in high performance computing and exascale environment, as you heard in the video, for over 10 years. So we have dealt with very large data sets and how to compute in technical computing environment, how to compute with those large data sets efficiently. We've been working with cloud providers, Amazon Web Services included, in order to optimize the infrastructure so that it can deliver value at lower cost. And finally, Intel is a big promoter and contributor to open source. We are the one of the largest contributors to Linux, and we are also now the largest contributor to OpenStack and contributing to Hadoop as well. So, as you bring these 3 trends together, that is what's allowing for the cost reduction that we are seeing for data analytics, where it used to be tens of thousands of dollars per terabyte of analysis. We just saw how you can do 100-core, 100-machine analysis on $7.50, less than the cost of a movie. So the areas I'll talk about are the optimizations and the things we are putting in as it relates to storage, server, network, and software. You saw a great flow from John earlier where he was talking about data collection, he was talking about data storage, computation, and collaboration and access. And I'll refer to each one of them as I go through this. So, in the Intel Xeon processor in the E5 line, we have put several optimizations that actually allow for scale-out architecture to perform at the best possible value it can. And I will refer to a few of the details around advanced vector extension technology, turbo boost technology, and AES and I instruction set using advanced encryption standard, and what performance profile they are providing in order to allow for the scale-out environment to work. So to start with, in the AVX instruction set, we have been innovating on instruction sets for decades. This is in that series of instruction sets, and often in technical computing, you heard about HPC use cases. You're dealing with large numbers, and you're doing a lot of floating point analysis. And in using these instruction set, now you can do more processing because you have you're increasing essentially the number of floating point operation you can do per clock cycle and doubling it up. So if you're dealing with technical compute use cases, you will see an increase in performance, and we've worked with AWS to kind of have that available in that infrastructure. I'll talk about turbo boost. So often cases we heard how during the day the cluster might be performing and being used very efficiently, and in the evening the cluster might not be used that efficient with that much data, because not that much data is streaming in. So how do you allow for more efficient power envelope and thermal envelope in that processing so that the total cost of infrastructure is lower, which is eventually what gets passed down to the user, so they can do more processing. And with turbo boost technology, what we do is we are able to, on as needed basis and based on OS request, improve the frequency of the core and allow for more processing to be done. But once it is done, to be brought back to what is the average power and thermal envelope, so that over the long run, when the core is not being used in a computationally intensive environment, you do not have the kind of power and thermal usage that you would have when the frequency was higher. So it allows for more optimized infrastructure to be used. And then finally, we heard about storage. Now, one of the things in storage is around data encryption. Data at rest needs to be protected. Encryption often has had a significant overhead in terms of processing cycle. And we introduced AES and I instruction sets, which are 7 instructions, but they're a pretty powerful one. And they provide 10x performance improvement over doing AES encryption. So often cases, what we see is the cost of encrypting data at rest is neutralized by the performance benefit you get by using the instruction set. And we work with our ecosystem so that that instruction set is being used when you encrypt the data on some of the environments you'll be working on. So this allows for not just to have acceleration on encryption, but protect against attacks like side channel attacks, where the malware or the threat tries to detect the interaction between memory and the core. And by using this instruction set, we actually protect against those kind of threats in the encryption processing. So when you combine these value proposition, what do you get? As you use the E5 2600, we ran a Terasort benchmark using 1 terabyte data. And what you see is a performance benefit by moving on to the Xeon E5 2600, 50% reduction in the time that it takes. Further performance boost can be had by using SSDs for storage. So going back to the point about storage that John mentioned, the next in the cycle is compute. And when you're running Hadoop clusters, you are doing a lot of parallel compute where there's an I/O data movement going on between these cores. And that is where 10 gig E reduces the time taken by additional 50%. And if you were using Intel's distribution for Apache Hadoop, where we have put additional performance optimizations that are tied to silicon, there is an additional 40% performance benefit to be had. So, you start from a Terasort over 1 terabyte that would take 4 hours on the previous generation processor, and bring it down all the way to less than 10 minutes by using all of these optimizations. And they are all available for use in Amazon Web Services, or at least most of them are. And what we are seeing is as more and more applications end up being driven by mobile user, the amount of data that's getting generated is increasing. Most of that data is getting collected in the cloud environments like AWS. And then the new business models that are actually making use of that data and then offering new services based on that data are coming up. And some of the examples were mentioned earlier by John. And with that, I would encourage you to give this a try. You have 600 hours of free supercomputing time made available on AWS for you. So if you're a user of Hadoop, go ahead and expand your cluster and try out with bigger data sets. If you're not a user of Hadoop, this is a great time to try it because there's an easy way to get started at no cost. Thank you.